Donald Lee Smith died a few years ago. He is famous for his high-power, self-powered free energy designs. There are several videos on the web showing some of his lectures. He produced one PDF document, and in May 2004 he was granted one patent. Don stated clearly in one of his lectures that he never did disclose the full details of his designs. However, Don says that he discloses enough for somebody who is experienced in radio frequency electronics to be able to deduce the things which he does not disclose, and so build a device for his own use. If that is the case, then anybody who has succeeded in doing that has kept very quiet about it afterwards, which would be understandable. Don produced at least 48 different designs which draw energy from what Don prefers to call the ambient background. His devices are capable of supplying kilowatts of excess energy, and in most cases they do not require any input energy to be supplied by the user. Don's work is subtle and not easy to replicate. It is based on the principle that the power output of a circuit increases with the square of the frequency and the square of the voltage. So if you double the frequency and double the voltage, then the output power goes up and becomes 16 times greater. As a result of this, Don's best known design uses a neon sign transformer circuit, which raises the frequency to about 35,000 cycles per second and raises the voltage to anything from 2,000 volts to 12,000 volts, giving a power output is physically quite small and yet has an output of 160 kilowatts. That's 8,000 volts at 20 amps from an input at 12 volts 1 amp. That is, the output power is more than 13,000 times greater than the input power. Consequently, his designs are for experienced developers only. Don Smith considered himself to be self-taught. He says that his understanding comes from the work of Nikola Tesla, as recorded in Thomas Martin's book, The Inventions, Researches and Writings of Nikola Tesla. This book can be downloaded from freeenergyinfo.com as a PDF file. Don states that he repeated each of the experiments found in the book, and that gave him his understanding of what he prefers to describe as the ambient background energy, which is also called the zero-point energy field. Don remarks that he advanced further than Tesla in this field, partly because of the devices now available to him and which were not available when Tesla was alive. Don stresses two key points. Firstly, a dipole can cause a disturbance in the magnetic component of the ambient background, and that imbalance allows you to collect large amounts of electrical energy using capacitors and inductors, which is a fancy name for coils. Secondly, you can pick up as many powerful electrical outputs as you want from that one magnetic disturbance, without depleting the magnetic disturbance in any way. This allows massively more power output than the small power needed to create the magnetic disturbance in the first place. This is what produces a coefficient of performance greater than 1. And Don has created nearly 50 different devices based on that understanding. Don has a website, or perhaps I should say Don had a website, but you will find that it's been taken over by Big Oil, who filled it with innocuous, similar sounding things of no consequence, apparently intended to confuse newcomers searching for information on Don's designs. The present situation in 2019 is that few people understand Don's designs fully, and I myself fall into that category. High voltage components are expensive and hard to find, and high voltages are dangerous. However, we look at one of his many designs and try to understand it as best we can. This is his tabletop device. It's a very high-powered generator. It produces a self-powered output of 160 kilowatts, which is enough to supply all the electrical needs for a row of houses. That's a row of 20 houses. The device is effectively a Tesla coil system, and so the normal electromagnetic effect of the ratio of number of coil turns does not determine the effect between the coils. His demonstration device looks like this. There's a battery which you don't see in this picture feeding this device here, which is a DC to AC alternator producing mains voltage. This device here is a variac variable transformer, which allows him to adjust the voltage applied to this device, which is a neon sign generator circuit, which steps up the voltage and steps up the frequency. The output from that is fed then via some tuning components through these brown wires to a few turns of what is effectively the primary winding of a Tesla coil. That's on a tube which can be slid in and out of this outside, difficult to see second coil here. The second coil is 3 inches in diameter and stands up on its own because it's made of very stiff wire. The output is passed on to some other components, and some of which are 4 very large capacitors wired surprisingly in series, though it doesn't look like that in the photograph, but they are wired in series to give 8,000 volts of capacitance, which allows a 20 amp output to be fed on to equipment through the connector panel here. This coil here is a choke, smoothing the output somewhat, but the interesting part is this second part here, this second winding on the choke former, is not used anymore. It was originally used to feed power back to the battery and keep it charged, but it was found that if the leads to the battery are the right length, you don't need that at all. So this coil here is unused in this particular demonstration piece of equipment. This device is not the easiest thing in the world to understand. Here is the circuit diagram. Right, the circuit diagram here shows you the battery feeding through a diode a DC to AC inverter, which output is fed to the primary coil here, which is shown on the outside of the secondary coil, which is this rectangle here. In his actual implementations, he always puts the primary coil inside the secondary coil. Not that it is critical in any way, it isn't. He has a third winding here, which is fed on to other circuitry, but the L2 secondary coil has got a capacitor across it and a variable resistor connecting to earth, and those are used to tune the operation of the L2 coil, the secondary coil. The tertiary coil here feeds on to a bridge, but not an ordinary bridge, it's a tuned bridge. The capacitor and variable resistor across the input to the bridge are used to tune the bridge to resonance with the previous circuitry. The output is then fed through a resistor divider pair to earth and on to an oscillator which drives the primary of a step down transformer to give an output which is very substantial. Now that's the circuit, and it's not a simple circuit. There are some very important points to be made here by Dom Smith in how this thing operates, and we need to pay attention to them. Grasping these points may make a considerable difference to our ability to tap into the excess energy available in our local environment. There are 4 points worth mentioning: voltage, frequency, magnetic to electric relationship, and resonance. Let's start with voltage. We tend to think of things with an intuitive view, generally based on fairly simple concepts. For example, we automatically think that it is more difficult to pick up a heavy object than to pick up a light one. How much more difficult? Well, if the object is twice as heavy, it would probably be twice as much effort to pick it up. This view has developed from our experience of things which we have done in the past, rather than on any mathematical calculation or formula. Well, how about pulsing an electronic system with a voltage? How would the output power of a system be affected by increasing the voltage? Our initial off-the-cuff reaction might be that the power output might be increased a bit. But then hold on, we've just remembered that watts equals volts times amps. So if we double the voltage, then we would double the output power. If we thought that, then we would be wrong. Don Smith points out that as capacitors and coils store energy, if they're involved in a circuit, then the output power is proportional to the square of the voltage used. Double the voltage and the output power is 4 times greater. Use 3 times the voltage and the output power is 9 times greater. Use 10 times the voltage, the output power is 100 times greater. This is a graph of the way that voltage alters, or output power alters with voltage. The graph itself is an exponential graph, and it goes up rapidly. So Don says that the energy stored multiplied by the cycles per second is the energy being pumped by the system. Capacitors and inductors temporarily store electrons, and their performance is given by formulas. For a capacitor, watts is equal to half of the capacitance multiplied by the square of the voltage multiplied by the cycles per second. In the case of an inductor, watts is equal to half of the inductance times the current squared times the cycles per second. You'll notice that where inductors, that's coils, are involved, then the output power goes up with the square of the current. So if you double the voltage and double the current, you'll get 4 times the output power due to increased voltage, and that increased output is increased by a further 4 times due to the increased current, giving 16 times the output power. Let's take a look at frequency. You'll notice from the formulas that the output power is directly proportional to the frequency called Hz or Hertz. The frequency is the number of cycles per second or pulses per second applied to the circuit. This is something which is not intuitive for most people. If you double the rate of pulsing, then you double the power output. When this sinks in, you suddenly see why Nikola Tesla tended to use millions of volts and millions of pulses per second. However, Don Smith states that when a circuit is at its point of resonance, resistance in the circuit drops to 0, and the circuit becomes effectively a superconductor. The energy for such a system which is in resonance is watts is equal to half times capacitance times the voltage squared times the cycles per second squared. If this is correct, then raising the frequency in a resonating circuit has a massive effect on the power output of the device. The question then arises, why is the main power in Europe just 50 cycles per second and in America just 60 cycles per second? If power goes up with the frequency, then why not feed households at 1,000,000 cycles per second? One major reason is that it's not easy to make electrical motors which can be driven with power delivered at that frequency. So a more subtle frequency is chosen or a more suitable frequency is chosen in order to suit the motors in vacuum cleaners, washing machines, and other household equipment. However, if we want to extract energy from the environment, Then we should go for high voltage and high frequency. Then when high power has been extracted, if we want a low frequency suited to electric motors, we can pulse the already captured power at that low frequency. It might be speculated that if a device being driven with sharp pulses which have a very sharply rising leading edge and a very sharply dropping trailing edge, that the effective frequency of the pulsing is actually determined by the speed of that rising edge, rather than the rate at which the pulses are actually generated. For example, if pulses are being generated at, say, 50,000 per second, but the pulses have a leading edge which would be suited to a 200,000 cycles per second pulse train, then the device might well see the signal as a 200,000 cycles per second signal with a 25% mark space ratio, the very suddenness of the applied voltage having a magnetic shocking effect equivalent to a 200,000 cycle per second pulse train. Alright, let's take a look at the magnetic to electric relationship. Dunn states that the reason why our present power systems are so inefficient is because we concentrate on the electric component of electromagnetism. These systems are always coefficient of performance less than 1. That is, the output power is always lower than the input power, as electricity is the losses part of electromagnetic power. Instead, if you concentrate on the magnetic component, then there is no limit on the electric power which can be extracted from that magnetic component. Contrary to what you might expect, if you install a pickup system which extracts electrical energy from the magnetic component, you can install any number of other identical pickups, each of which extract the same amount of electrical energy from the magnetic input without loading the magnetic wave in any way. That gives you unlimited electrical output for the cost of creating a single magnetic effect. The magnetic effect which we want to create is a ripple in the zero-point energy field, and ideally we want to create that effect while using very little power. Creating a dipole with a battery which has a plus and a minus terminal, or a magnet which has a north and south pole, is an easy way to create an electromagnetic imbalance in the local environment. Pulsing a coil is probably an even better way, as the magnetic field reverses rapidly if it's an air-cored coil, such as the Tesla coil. Using a ferromagnetic core to the coil can create a problem, as iron can't reverse its magnetic alignment very rapidly, and ideally you want pulsing which is at least 1,000 times faster than iron can handle. In a typical Tesla coil, the primary coil is much larger diameter than the secondary coil, which is down the middle. If, for example, 8,000 volts is applied to the primary coil, which has got 4 turns, then each turn would have 2,000 volts of potential across it. Each turn of the primary coil transfers electromagnetic flux to every single turn of the secondary winding, and the secondary coil has a very large number of turns. Massively more power is produced in the secondary coil than was used to energize the primary coil. A common mistake is to believe that a Tesla coil can't produce serious amperage. If the primary coil is positioned in the middle of the secondary coil as shown above, then the amperage generated will be as large as the voltage generated. A low power input to the primary coil can produce kilowatts of usable electric output power. We then come to the interesting topic of resonance. An important factor in circuits aimed at tapping external energy is resonance. It can be hard to see where this comes in when it is an electronic circuit which is being considered. However, everything has its own resonant frequency, whether it's a coil or any other electric component. When components are connected together to form a circuit, the circuit itself has an overall resonant frequency. As a simple example, consider a swing. If the swing is pushed before it reaches the highest point on the mother's side, then the push actually opposes the swinging action. The time of one full swing is the resonant frequency of the swing itself, and that is determined by the length of the wire or ropes connecting the seat of the swing to the swing frame. The wire length holding the seat, and not the weight of the child, nor the power with which the child is pushed, has an effect. Provided that the timing is exactly right, a very small push can get a swing moving in a substantial arc. The key factor is matching the pulses applied to the swing, that is, to the resonant frequency of the swing. Get it right, and a large movement is produced. Get it wrong, and the swing doesn't get going at all. At which point critics would say, see, swings just don't work. This proves it. Establishing the exact pulsing rate needed for a resonant circuit is not particularly easy because the circuit contains coils. The coils have inductance, capacitance, and resistance. The circuit also contains capacitors, which have capacitance and a small amount of resistance. And it contains resistors and wires, both of which have resistance and some capacitance. These kinds of circuit are called LRC circuits because L is the symbol used for inductance, R is the symbol used for resistance, and C is the symbol used for capacitance. John Smith provides instructions for winding and using the type of air core coils needed for a Tesla coil. He provides quite an amount of information on this device, which we're taking a look at, and without his description of the device it would be difficult to understand its construction and method of operation. As I understand it, the circuit of what is mounted on his board is as shown here. You have a 12-volt battery feeding through a diode to a DC to AC inverter. You have an optional variable voltage transformer which allows you to control the voltage applied to the neon tube driver circuit. It incidentally has two outputs, so two diodes are used to connect both sides of this particular unit to give an output. The output is used to charge a capacitor C. A spark gap triggers when the voltage across C gets big enough, and that operates a major pulse to the L1 primary coil of your Tesla coil, which in this instance is shown split in two because that's the way that John has it physically constructed. A capacitor then across the output of the circuit is fed across and feeds a very large capacitor. This is an 8000 volt 2 microfarad capacitor, which is large and expensive. And then there is a suppressor coil, which is not too important but is used in this circuit to give the output, which can be 8000 volts at 2 amps, 8000 volts, 2 amps, 160 kilowatts. This is a major output. Anyway, the electrical drive is from a 12-volt battery, which you don't see in the photograph. Interestingly, Don remarks that if the length of the wires connecting the battery to the inverter are exactly 1/4 of the wavelength of the frequency of the oscillating magnetic field generated by the circuit, then the current induced in the battery wires will recharge the battery continuously, even if the battery is supplying power to the circuit at the same time. So this is how the operation goes. You've got a battery feeding sine wave inverter. You've got a variable transformer allowing you to specify the AC voltage applied to your neon tube driver circuit. The circuit steps up the frequency and steps up the voltage. You've got some components here which help tune to a resonant frequency, and the output through these brown wires goes inside this inner plastic tube and comes out to give the few windings of the primary winding. This slides inside the secondary coil. The secondary coil supports itself. It's not on any former. It's made of thick wire, and the turns are separated, and in the middle the tap is taken off from the secondary coil and fed on to feed the output circuitry. Interestingly, this is the choke to smooth the output, and this coil here was originally used to power a circuit which fed the battery and kept it up to its full voltage. But in this circuit nowadays, that coil is redundant. It is not used at all. Now, this is the way that the particular circuit operates. You may not see it in the circuit itself very clearly, but there is a spark gap or gas discharge unit here. It looks like this, and it operates inside an inert gas contained inside the container. Now, the thing you need to understand about the earth is that in the circuit diagrams, when an earth connection is mentioned with any of Don Smith's devices, we're talking about an actual wire connection to a metal object physically buried in the ground, whether it's a long copper rod driven into the ground, or an old car radiator buried in a hole like Tariel Kapanadze likes to use. When Thomas Henry Morey was performing his requested demonstration deep in the countryside at a location chosen by his skeptics, the light bulbs which formed his demonstration electrical load glowed more brightly with each hammer stroke as a length of gas pipe was hammered into the ground to form his earth connection. It should be remarked that since John purchased his neon tube driver module, that newer designs have generally taken over completely, especially in Europe, and these designs have built-in earth leakage current protection, which instantly disables the circuit if any current is detected leaking to ground. This feature makes the unit completely unsuitable for use in a Don Smith circuit, because there the transfer in current to the ground is wholly intentional and vital for the operation of the circuit. However, you can easily make your own neon style module equivalent with a car ignition coil if you want to. You have a 12-volt battery. It's feeding a capacitor to give a smooth input to an ordinary 555 chip. This part forms the oscillator, and the output of the chip goes to the gate of a P-type FET transistor, which has a protective diode across it to keep the transistor safe. The transistor drives current through the primary of the car coil, which is a high voltage step-up transformer, and that's passed in through a diode, high voltage diode, with a tiny capacitor across it to give the stepped up output high frequency voltage. This is a simple circuit which you can use to drive the L1 primary of a Tesla coil style transformer. This looks ever so simple and straightforward, but there are some subtle details which you need to be considered. Much more on this is in the Chapter 3 document, PDF document on freeenergyinfo.com if you're interested. However, making a high power device like this is not easy to do, and very few people have accomplished it. But there is an easier approach if you're not interested in powering a row of 20 houses. A Ukrainian student, I am Solev, was not satisfied with the many errors in conventional science, and he decided to write his PhD dissertation on the lack of information on free energy. Just like Don Smith, his experimentation was with the Tesla coil, but he avoided expensive high voltage components, and while his output power was much lower, his objective was to show that free energy exists. The translation for his application is shown below, and thanks is due to Howard Haley for making this translation. His paper was entitled Electric Power Generation System High Frequency, and he talks in his paper about he says that currently there's a great deal of information about devices after which activation, in whatever working field, the process of relaxation, output energy, is in excess of the input energy used. For example, the production of thermal energy observed in the oxygen-hydrogen electrolyzers for normal and heavy water, and the electric discharger, and the vortex heat generators. In the late 1980s, Stanley Mayer's patent for the water fuel cell that allows the conversion of ordinary tap water into hydrogen oxygen with far less expenditure of energy than would be required by conventional electrolysis, and in much greater quantity than expected with simple electrolysis. His explanation of the results is based on the resonant electric field effects on water molecules. Later, Don Smith built a number of devices based on Tesla's experiments, mostly with high output power. In his articles, he notes that he repeated each of the experiments found in the Tesla books, and this gave him his understanding of ambient background energy. His objective was to repeat one of the above methods of obtaining energy, to test whether these devices really do work. For this, he says, we implemented the circuit of the Don Smith device from his patent of 1999, where his generator can achieve an output of 15 kilowatts. This is the circuit that he shows. Now, I'm not aware of any patent from Don Smith which contains this particular circuit diagram, nor of any patent in 1994. But then, perhaps he's got one that I don't have. The basic materials and method of research, he says, the main elements in the schematic of Figure 1 is an air core transformer with the windings numbered 6, which is the primary, 6A, which is optional, 7, which is the secondary. For this study we prepared primary L1, secondary L2, and an additional L3 coil according to the details in this following table. For the L1 coil, the coil length is 5.5 or 5.5 centimeters, 55 millimeters. The number of turns on the coil is 8. The diameter of the coil former is 5.5 centimeters. The finished coil had a resistance, DC resistance of 0.1 ohms. The length of copper wire used to wind the coil is 1.4 meters, and the wire diameter used was 2 millimeters. For the secondary coil, he had a 32 centimeter length when it was finished. It took 463 turns to do that. The diameter of the former was 5.1 centimeters. The DC active resistance of the finished coil is 4.2 ohms. The length of copper wire used in winding the coil was 69.1 meters, and the wire diameter used was 0.65 millimeters. His additional coil, L3, was 6 centimeters long. It had 10 turns in it. It had a former diameter of 5.6 centimeters. The resistance measured in DC ohms when checked out after winding was 0.1 ohms. The length of wire needed was 1.8 meters, and the wire diameter was 1.2 meters. Sorry, 1.2 millimeters. They used a program to calculate the expected results from his windings and so on, and he quotes the actual results here. Then he goes on to do a test. He placed the L1 winding at the bottom of his L2 winding. This sketch I've done here is has the L1 coil a little high. It actually should be pretty much on the base board itself, because he says he put the primary at the base of the secondary. Now this is the circuit that he used. He applied 14 volts DC, put a capacitor across it, and then he developed this very complex circuit which comprises of 2 resistors and 1 transistor and 2 coils. Very difficult. But that circuit, where he has a 2.2k resistor and a 160 ohm resistor feeding the base of the transistor itself, the transistor is an NPN bipolar type, driving the L1 8-turn primary of his system. This is the arrangement that he used for his test. He measured the voltage across the secondary, 463 turn secondary, and found it was around 700 volts. So you want to be careful dealing with systems where the voltage gets stepped up. This is not actually a toy. Now, the experimentally determined values of voltage was that the frequency that this circuit generated was 1.1 megahertz. That is, this circuit oscillates at more than 1,000,000 times a second. So as well as having a very high voltage, it has a very high frequency coming out of it. He says when connecting the circuit in figure 2 to the constant power supply, the power consumption was 0.3 amps, that's 300 milliamps, and that at 14 volts is 4.2 watts of power being pushed into the circuit. When you look at the output, you have 300 milliamps at 700 volts, which is 210 VAR. That is considerably extra power output. They used bulbs as the assessment of output. In all these figures, 3, 4, 5 and 6, the bulb was used, and they used the brightness of the lamp to give you an indication of the approximate output power. He used various different lamps from 0.3 watts to 21 watts. With this circuit in figure 3, 0.3 watts did not lead to lighting in the bulb, although 4.2 watts of energy was being pushed into the circuit. They decided to add on a third coil, the L3 coil of 10 turns. They put it in the upper third of the L2 coil physically. A 6 volt 3 watt amp lamp was connected to the additional coil L3, but the lamp only showed a subtle glow. Then they decided to put a capacitor in series with the winding L2. So L2 goes through a capacitor to earth. The L3 10 wind coil is still feeding the lamp. The lamp became brightly lit, and in 4 to 5 seconds it burned out even though it was a 21 watt 12 volt bulb. The consumption of current for the circuit was 1.2 amps typically. You got a very similar result when you put a tungsten lamp in series with the capacitor that's going back to earth from the L2 coil. 21 watt 12 volt bulb in that position burnt out in 4 to 5 seconds. The current consumption in the circuit certainly didn't go above 2.3 amps. His conclusion was that exploratory studies confirm the existing scientific thought that the processes of input and output transmission of electricity using high voltage, high frequency electromagnetic field radiation phenomena requires further deep theoretical and experimental studies. And this interesting thing about this paper from our Ukrainian student is that the input voltage is so low, at a mere 14 volts, although of course the output voltage is much higher and is also at more than 1,000,000 cycles a second. The final diagram is interesting in that his 21 watt 12 volt bulb was destroyed in just a few seconds. The measurement of current through the bulb was supposedly 2.1 amps, while the bulb's design current is 1.75 amps. That difference between 1.75 and 2.1 amps is not enough to have destroyed the bulb so rapidly. So the problem will have been that the bulb wattage was exceeded very severely. Earlier, the voltage across the L2 coil was measured at 700 volts, so there may have been as much as 700 volts applied to the 12 volt bulb. If 700 volts were applied to the bulb and a current of 2.1 amps flowed through the bulb, then the dissipated power in the bulb would have been as much as 700 times 2.1, which is 1,470 watts, which is 70 times the rating for the bulb, and it's more than 1 kilowatt. Please don't be misled by the 14 volt input voltage, as this circuit steps up the voltage and it might kill you. It's said that the high frequency of 1.1 megahertz makes the output harmless to humans. I have not tested this, and you really need to be careful around any high voltage circuit. A point which he missed in his dissertation is the fact that the positioning of the L1 primary coil along the length of the L2 secondary coil has a major effect on the output amperage. So positioning the L2 coil in the middle of the L1 coil should increase the output power very considerably. The lamp used as the load is essentially a resistive load. I don't know enough about the subject, but putting a simple step-down air core transformer in place of the bulb should lower the output voltage and increase the available output current very considerably. It might well be worth testing this simple circuit. Let me stress that this presentation is only for experienced developers
who are familiar with high voltage circuits. If you're not familiar with electronics, there is a tutorial at www.freeenergyinfo.com/tutorial.pdf. The South African developer says, I have built the Solovay replication as close to his version as I am able to do with the materials available to me. Solovay's original circuit is shown here. It's very simple, very straightforward, driven typically by a 12-volt battery, which of course can charge up to 14 volts if necessary, and it's just a simple resistor divider feeding the base of a transistor, which has got two coils which provide feedback to itself and generate a magnetic field. In his presentation, the circuit diagram there, is his figure number 2. The South African developer says, this is my slightly modified version. I've introduced a variable resistor to control the current to the base of the transistor, and this is a photograph of the actual implementation as he has particularly built it. I'm using a TIP 3055 transistor. I've tried a large range of transistors, MJE 13009, TIP 132, and all sorts of others, and the only ones which work at all are the 2SC 3552, which is a 1000-volt transistor, and the TIP 3055, which is the best by far. These are my coil details, and in this table he shows the particular winding type and lengths used in the different versions of the coils. He says, initially I tried Solovay's primary coil L1 with 8 turns and a diameter of 700 millimeters. I beg your pardon, of 70 millimeters, but had far better results with only 3 to 4 turns. My criteria for assessing these things were the strength of the corona at the top of the secondary coil, L2, and the degree of fluorescence produced in a nearby handheld compact fluorescent lamp, as well as the distance of the lamp from the coil. This is a photograph here of the implementation. That's L2 there, and around it is L1. And he says the white wires are not connected. They're just being used as spacers. I then tried a larger primary L1 coil with many more turns of thicker copper wire, on which I could vary the number of turns and also the position vertically of L1 relative to L2. I found that the larger diameter seemed to produce an enlarged magnetic field, which was better, but the wire thickness and the vertical position in this instance was not at all critical. Interestingly though, in every variation the optimum number of turns in the L1 coil was 3 to 4. I presume that this is the best resonant match with the secondary L2 coil in its present form. This is a photograph of his L1 coil, which can be adjusted. You can adjust the position vertically depending on where he clips the two wires, and the number of turns in the coil as the number of turns between the two clipped connections. And he says this is typical of the fluorescence produced in a compact fluorescent light bulb and the corona produced at the top of the coil. He says, I then measured the voltage at L2 empirically and found it able to charge a 1 microfarad capacitor very rapidly to 2000 volts. I presume the rectified AC voltage to be far higher, at least in the multi-kilovolt range. I feel that the formula mentioned by Solovay, namely U2 equals UM divided by N1 times N2, does not necessarily apply to this type of Tesla configuration, so I question his calculation of 700 to 800 volts. I was unable to measure the frequency accurately with my handheld oscilloscope, but the reading which it displayed seemed to hover around the 300 kilohertz mark. It may be much higher. I then configured a capacitor to withstand high voltages of, by calculation, variable between 0 picofarads and 800 to 900 picofarads. The capacitor rather, would be used in this position with a lot of high voltage diodes forming a single high voltage diode in the particular circuit. His construction of this variable capacitor is shown here in this photograph. In all subsequent tests, he says, I found that the introduction of this capacitor between L2 and ground, which admittedly I could tune to optimize resonance, increased the current draw from the supply battery to such a degree that 3 TIP 3055s in parallel exploded and burnt out in seconds. They can each handle 15 amps, so I measured the current as accurately as I could with both digital and analog meters, and found that it could easily exceed 40 amps. This is why I've used such a massive heatsink. Also, the voltage present at the top of L2 immediately drops when the capacitor to ground connection is present. This can't be good as far as coil L3 is concerned. He says, I used the same lamps as Solovay, that's 21 watts, 12 volts, in series with the capacitor from L2 to ground, namely there. So between L2 and the capacitor connecting to ground is where the bulbs are located. The lamp burnt out in seconds, but what I feel that Solovay has failed to indicate in his paper is that the current draw does not remain as is measured 0.3 amps drawn from the supply battery when a capacitor is connected to ground, as shown in this diagram. This means that although the lamp is experiencing a current of 2 or more amps, one cannot calculate overall wattage based on the product of the voltage times the current, when the supply current is now extremely high. I then moved on to the next phase, which included a lamp across L3. This is the extra winding here. It's 10 turns feeding the lamp, going through its variable capacitor to ground. The lamp burnt out again, and I introduced a high wattage variable resistor of 100 ohms in the supply line to limit the possibility of high current and to protect the transistor by that mechanism. He says I usually had the variable resistor set to 50 ohms. So he's talking about a high wattage 50 ohm resistor in that position. I then decided to remove the capacitor to ground and replace it with a spherical aluminium globe. This provides capacitance to the ambient surroundings, which proves to be a considerable improvement as far as the performance of L3 is concerned. It also reduces the corona discharge losses so that the lamp now burns brightly and the compact fluorescent lamp still fluoresces when held near the L2 winding. This indicates that the voltage at L2 is no longer dropping in spite of the load imposed by L3 and the lamp. This is the arrangement at the top of the L2 coil. So the unit with his aluminium sphere at the top looks like this. He says, I was able to dispense with the 100 ohm resistor as the current draw from the 12 volt supply battery was now down to 2 amps, which is a much more reasonable amount, but still more than Solovay's 0.3 amps. Having got thus far, I moved on to Don Smith's next stage, which was to replace the lamp with a bridge rectifier on coil 3. The black wires in this case are just spacers, they're not connected, and the lamp operates well. Voltage across the capacitor rose to well over 1000 volts, so I stopped the experiment as I was afraid it would damage my digital meter. I then thought of trying 2 extra coils simultaneously, and I did that by putting a second bridge rectifier over the black wire coil, which had previously just been used as a spacer. With that arrangement done, the circuit became this here, and now there are 2 simultaneous DC outputs of 1500 volts each. I put a voltage divider across my analog meter to measure this. Here you can see my meter set to the 1000 volt range. I realize that this is a low power version of Don Smith's circuits, and one cannot expect much from it. I know that Don Smith, in order to achieve very high outputs in terms of kilowatts, relied very much on resonance in his circuits. What I'm investigating here is simply Solovay's attempt to demonstrate that a greater output than input is possible. He did not seem to carry it any further, as he had achieved his objective as part of the university degree attempt which he was making. From my experience with these high voltage pulses, or in this case high frequency AC circuits, is that it is possible to achieve very high voltages from a simple 12 volt system, but that in general there is not very much power available unless one can achieve the advantage of resonance in some form or another. In a very basic experiment, I tried the following circuit, which is just a simple battery charging circuit, but it's not charging any load directly. This is the circuit here, as before, with 2 L3 coils, 2 rectifiers, one supplying the battery to be charged, and one feeding back to the battery which is driving the circuit. He says using that, after 1 hour of operation, the drive battery had dropped from 13 volts to 12.9 volts, and a very dead 12 volts 7 ampere battery had risen from 3.3 volts to 6.3 volts, and it's holding that 6.3 volts now. I'm sure that a battery in better condition would have charged even better, and I will try it. When a battery charge load is applied to the extra coils, the compact fluorescent lamp will no longer fluoresce. I observed that a real earth connection has helped a little. My current draw from the 12 volt battery supply using both extra coils in this configuration is only 0.4 amps, which is 400 milliamps. This experiment suggests to me that one might make many extra pickup coils like the above, of 3 to 4 turns each, placed along the length of L2 with L1 at the very bottom. This would bear out Don Smith's claim that one can draw multiple sources of energy from an inductive magnetic field without increasing the load on the supply. There's obviously much more scope for experimentation with this type of low voltage solid state Tesla coil. He says, I've retested and duplicated my results so far, and in the process I discovered something of small significance. Developer Ming Kao has mentioned in his comments, which are in www.freeenergyinfo.com/chapter3.pdf, page 186, that he found an improvement when he placed the primary coil and the pickup coil far apart on opposite ends of his secondary coil L2. I did this and found a definite increase in voltage output. What I think is happening is that the section of L2 between L1 and L3 is being increased. This is a photograph of the arrangement that he's using. He says, I have vertically flipped coil L1 so that the 3 active windings are now at the bottom, and I moved the pickup L3 right to the top of the L2 coil. I also noticed that the output in this configuration increased substantially when I removed the aluminium globe and just left the open end of the Perspex tube at the top of L2. This is good news, as these metal spheres are not easy to find. What has taken place as I have experimented is that I have gradually dispensed with all capacitive components with improved results. This is important to me, as I seem to have moved from LC resonance to resonance between the coil windings only. As LC resonance is very difficult to achieve in complex circuits, whereas coil-to-coil resonance can more easily be achieved by calculation and careful measurement, this discovery is welcome. The last stage is an interesting one, since I now felt that I was no longer dealing primarily with LC resonance, and therefore the magnetic field was more dominant in energy transfer than was the electric field. I thought of Don Smith's multi-coil power source. I wound another coil with materials I had in order to try coil-to-coil energy transference. This new coil is 50 millimeters in diameter, and the winding is 400 millimeters in length. Wound with 0.5 millimeter diameter enameled solid copper wire, this has resulted in 800 turns, and I will call this coil L2B. I have it standing, as you can see, next to the primary device, and the only connection is from the bottom of L2B to common ground. So in other words, he's saying this is the only connection to this L2B coil. And he tested that particular configuration and found that the compact fluorescent lamp would light up from the L2B coil. At the top of the second coil in the first picture is a string of 10 1N4007 1000 volt diodes connected in series, and the voltage output to ground on both coils simultaneously is 2100 volt at each coil. I have moved the L2B coil up to 70 centimeters away from L2, which is as far as my wires would reach, and at that distance the voltage output of L2B remains 2100 volts. What this demonstrates to my satisfaction is that Don Smith's suggestion based on the following drawing here will work in practice. This drawing shows 5 L2 coils surrounded by one small number of turns L1 coil. He says, I have not yet come across any really successful replications of Don Smith's devices, so this is reassuring to me. What's interesting is that as I move L2B away from L2, the voltage drops and rises by increments of about 5 to 10% at incremental distances of about 20 centimeters. For convenience, the coils in a real construction would need to be much more closely spaced, but the width of the field is amazing. It also suggests that the arrangement of the coils should be done carefully and empirically. Something I wish to stress in closing, he says, is that I have in no case paid any attention to the quarter or half wavelength issue of the relative lengths of the primary to secondary wires, or ratios. None of my coils have any calculated wavelength ratios or measurements, and yet have achieved, for a low power solid state device, quite demonstrable results. I think that Richard Quick's essay on the practical aspects of resonance is most impressive and useful. It's reproduced below. But an issue I find unresolved is this: if the LC component of resonance is replaced by the magnetic component, then we're dealing with a longitudinal wave, which, as I understand, is a defining characteristic of cold electricity, and we're not dealing with a transverse wave. A standing wave, as determined by wavelength resonance, is essentially a transverse wave phenomena with clearly defined nodes. A longitudinal wave will not have nodes. This is a contradictory issue which is not yet clear to me, and maybe is a field worth investigating by other developers. Solovey's details are available via that link there, and this is the discussion of Richard Quick on the link up between coil lengths and resonance. I'll leave you to read that through, because it's worth considering carefully as you read, and it's fairly lengthy and very detailed. I suggest that you do take the time to have a read through it and consider what it is that's been said in that. So that concludes the presentation here in this video, which is primarily on the work of our friendly South African developer. So that indeed is the sum of this video.